Assalamu alaikum, guys. So today's lecture is the demodulation of frequency modulated signal. So frequency modulated signal demodulation is the topic. So frequency modulated signal demodulation. So this frequency modulated signal can be demodulated using a differentiator. We have seen in our in angle modulation where actually we describe the frequency modulated signal by frequency modulated signal. So here actually we represent our frequency modulated signal, right? Okay, so frequency modulated frequency modulation signal can be demodulated using a differentiator. Using a differentiator. See, we will illustrate how to modulate this FM signal in a differentiator. Say, let us say we have a signal ST, modulated signal we received, and we will pass through it a differentiator. Okay, so differentiator will look like this. So this will be expressed by this differentiator, and then output will be d by dt of st, which is actually the demodulated or original signal. So this is actually a differentiator. Okay, so let us draw write the frequency modulated signal. You have seen the frequency modulated signal in our original frequency modulated signal before we actually derive our narrowband or wideband signal. So this is the expression. So let me rewrite it again. So our frequency modulated signal ST can be write as AC cos twice by FCT plus twice by K of F M tau d tau. This is actually our FNC. So what we have to do, we have to transmit this signal through a differentiator. So we will actually pass this signal through a differentiator. We actually pass through. So we will actually pass through a differentiator circuit. So if you pass through this signal to a differentiator circuit, what will happen? We will actually have this signal d by t of st, then AC. So cos theta will be minus sine theta, right? Twice by FCT plus twice by K F integration of M tau d tau, right? Multiplied by, because this is not a theta, so d by dt of this part, twice by FCT plus twice by Kf 0 to t M tau d tau, which is nothing but, we will actually complete this. So minus AC sine twice by FCT 0 to t, 0 to t. And tau d tau. And here d by dt twice by fct will be twice by fc, right? Plus twice by kf. You see here, this equation in this here, we know d by dt integration of 0 to t m of tau d tau can be easily written as m of t, right? So we will actually write it here. So this will be nothing but twice by mt, like this. So what we can write, like interchanging this term, we can write it as minus AC. So actually we're taking this here, twice by FC plus twice by KRF m of t into this sine term, sine twice by FCT plus twice by KRF 0 to t of tau d tau. So here we can see that this is actually this term, this terminology, this one, whole term, this is actually the output of this differentiator, and this is actually the envelope of the output of the differentiator. Okay, so this is actually this one, the whole terminology is the output of the differentiator. And this one, if this is the output of this differentiator, this is actually the envelope of the output of the differentiator. This is actually the envelope of output of the differentiator. Okay. So this is the envelope distribution, and this amounts to be this AC, this amount, twice by plus twice by m of t. Here you can see that this envelope is nothing but a function of this term mt. Mt is the message signal. So the way message signal will be varied, the envelope will also be varied, like the amplitude modulation stuff. Okay. So this actually okay. So this is actually nothing but the envelope of this. So this envelope is nothing but the function of this variable message signal mt. Okay, so we can write it twice by AC FC plus KF m of t, which can be written as also, like if I write twice by AC FC, and we can write 1 plus K of F m of t and FC. Okay, so this term can be used. This is the terminology that can be used to recover our original message signal. So this can be used. This can be used to recover original message signal, right? Original message signal. MT. Okay, we can use this signal to recover our message signal. Now, to recover this message signal, there is because this will envelope dictation, which actually also very much similar to our envelope, the detection of our amplitude modulated signal means the envelope detection or successful envelope detection or no distortion. There should not be any overmodulation. That should be highlighted here. For envelope detection, the signal should not be overmodulated. Okay, should not be overmodulated. Okay, signal should not be overmodulated. Because if overmodulation happens, then signal distortion also happens. So, since overmodulation results in like phase reversal, okay, what the overmodulation do? Since overmodulation results in phase reversal. We actually seen in our amplitude modulation, right? Phase reversal, which actually do not occur or not arising due to from the carrier, from the carrier is actually happening because of overmodulation, not that the carrier phase changes. Okay. Okay. If we do not want this overmodulation do not happen, then this amount has to equal greater than has to 0, which is actually nothing but twice pi. So for condition, this is actually for condition for no envelope distortion, no envelope distortion. So this has to be twice pi. This amount has to be twice pi AC FC plus K of F M of T. That amount has to be greater than 0. If this is the case, then we know that FC has to be greater than equal to. So KF is the amplitude of maximum amplitude of M of T. Okay, so means actually the carrier frequency has to be the maximum amplitude of the MT. Amplitude of the message signal, right? Okay, now from our previous example, we actually seen, I'm not deriving this anymore. We have seen that del of F, the deviation, maximum frequency deviation, del of F, or del of F, what was the condition? So for del F, let me see what is the value of del F. It should be function of some M del F. Yeah, here. So by following this maximum frequency deviation, this equation, we'll be using that. We know that maximum del of F, del of maximum frequency deviation is nothing but the maximum value of Fit minus Fc. Okay, which is actually nothing but the maximum value of K of F of MT. which is nothing but for our case k of f, maximum value of m of t, which is actually this one. Okay, so we can write that fc will be much greater than del of f. This is actually the condition for no envelope distortion. So this is actually the condition for no envelope. This is actually the condition for no envelope distortion. Envelope distortion. Where the carrier frequency will be much higher than the maximum frequency deviation. Okay, so let us discuss about some example. Let us show an example. So imagine we have a carrier frequency fc, say it's 100 megahertz. Okay, and frequency, modulated frequency fm is actually 10 kilohertz, which actually the frequency of our message signal, for example, maximum of the modulating signal, and the modulation index beta is 10. So we know beta is nothing but del S by fm. Okay, so for this case del f will be nothing but the beta into fm. Beta is 10, fm equal to 10, actually 100 kilohertz, which is actually nothing but 0.1 megahertz. You see here for fc, which is actually in our case 100 megahertz, is greater than del of f, where this del f is nothing but 0.1 megahertz. In this case, so because the carrier signal fc is much higher than the maximum deviation of, so means there is no over modulation is actually happening here, means no distortion of in the envelope is happening here. Okay, so that's all for this lecture. Assalamu alaikum.